And we're ready to welcome the second workshop, which will be on the introduction to reinforcement learning. So RL for the familiar ones. And reinforcement learning uses an agent to perceive its environment, take actions, and learn through trial and error. So in this introductory workshop to RL, you will learn key concepts like agent, policy, environment, state, rewards, and such, and you'll get the opportunity to learn how to program them. So we're lucky enough to have Armin to present us with this intro, so I'll let Tim give a bit of background on him.
Sure. Sorry, I might have blanked out. Did you talk about the workshop itself, or should I speak about that as well?
Yeah, I just did, Tim.
Okay, sorry. thinking about the next ones. Okay, so we're very lucky to have Armin Najarpour Forushani. I hope I said that okay. Definitely correct me, Armin. So he is an AI specialist at AI Launch Lab, and very lucky to have him on the team. Armin is a PhD in biomedical engineering from Polytechnique Montreal, and a member of the AI team at iCompato. Is that how you say it?
Yeah, AI Compato.
Cool, great. So thank you so much, Armin.
Thank you so much, Monica and team, for introduction. So I'm going to share my slide here. Share my screen. If you can see it, right?
Yeah, maybe put a presentation mode if you prefer.
Presentation mode.
I think at the bottom, right where there's the Zoom bar.
Oh, yeah,
perfect.
Oh, okay, yeah, sure.
No, it's perfect. Thank you, Armin.
Thank you. So this is an introduction to reinforcement learning. So I will talk about the general concepts, and I think in the next workshop for the next Saturday, we can go a bit deeper into the more stuff like how to train the model. So in machine learning, we have basically three different tasks. We have supervised learning, we have unsupervised learning, and reinforcement learning. And so here, for example, classification and regression are forms of supervised learning. So we need to train train our model on a data set. And also for unsupervised learning, we also need data in order to get conclusion about how our data sets are grouped or clustered into a specific, parts of data can form a group, as Mo explained in previous workshop. So, but there is a third form of machine learning model called reinforcement learning that doesn't necessarily require to collect data. So, reinforcement learning interacts with the environment in order to learn. There are four main features of reinforcement learning. So reinforcement learning is mainly learning to make decisions from interaction with the environment. And instead of having labels or output as output to supervise the model, we have rewards that are distributed in the environment. And the interaction of agent to the environment is sequential. So we have time steps, step 1, 2, 3, and goes on. And so the learning procedure is online when the agent is doing it. There are some examples of reinforcement learning, like self-driving cars, industrial automation, making the robot to move, flying a helicopter, playing video game, or a financial decision like to hold, to buy, or to sell something, or medical treatment strategy. And all of these examples involve sequential decision making. This is a general framework for reinforcement learning. So we have an agent that interacts to environment, but this interaction has three main components. So the agent observes. Here states means, it is observation. You can consider state as something that agent observes from environment. And based on the observation, agent make an action. So we have action at time t, here t is time t. And in the next step, when agent goes to time t plus 1, agent receive a reward, which is shown by rt plus 1. And based on this sequential procedure, the agent tries to learn how to act in the future. So there are main components of, there are some core components for reinforcement learning: agent, environment, state, action, reward, and we talked about this first part, but I will go to more details about the reward in the next slide. We will also talk about policy and value function. So basically, agent is the learning algorithm. For example, if you have a robot, the learning algorithm in the robot is agent and not the robot itself. And the rest of the robot, or something which is separated from that learning algorithm, is accounted as the environment. Here, this is a kind of simple environment. So an agent can be placed in any of these positions. The O is obstacle, F is food. And this star here is an agent, which can be placed anywhere. And this 0, 1, 2, 3, 4, 5, 6, 7 are what agent sees. So we call it sensory information. And this is state. When we talk about state, is this sequence. So if we have, for example, starting from 0 to 7, we have obstacle, obstacle, F, So, and we consider something like a code, a binary code for each object. You'll have a binary sequence, and this binary sequence will be the input for the agent. And the agent can perform action toward each of these directions if the next step for agent will be an obstacle, so it cannot move toward that. But when it's empty, it can go on when it's food, it can also go to the place that food locates. So reward is a scalar feedback signal that we show it with RT, which is reward at time t. And it shows how well agent did at time t-1. And basically it shows the desirability of that action at a specific state. So the goal of reinforcement learning or agent is not to maximize the reward, because reward is already set by the environment, but the goal is to maximize something called return. And return is the summation or is the discounted sum of future reward, as we can mathematically show it in this way. And this gamma value is called discount. And this discount value trades off the importance of immediate versus long-term rewards. And if the gamma value is 1, so all the future values have the same have the same weight, and if it's less than 1, it puts a higher weight to the immediate reward compared to the current reward. Policy, and this is at the core of reinforcement learning. I think this is the most important thing that everybody should know. Policy. Policy is mapping from states to action, which is actually an agent's behavior. We show it with pi, and we have doing action when we are at state S. So this is the definition. And it's a kind of probabilistic mapping. And the agent, over time, when it interacts with the environment, it learns to improve the policy over time by starting with random action selection. So at the first starts with random action selection, and over time, when the policy is modified, it can we can say that the agent is learned and knows at which situation make which action. We to formalize it mathematically, there is a concept called value function. So value function is a definition, but it's mainly used as a main mathematical representation for reinforcement learning. And it shows the change of policy for maximum return. And usually two types of functions are used. One is state value function, the other is action value function. And the purpose of reinforcement learning, or as we talked before, is to find a policy that maximizes this value function. So the policy which can maximizes this value function is called optimal policy and is denoted by pi star. Mathematically, the state value function is actually the expected value of the return at state S. So at time t, we are at state S. For example, it's an observation, specific observation. And this is also defined based on the policy at that point. An optimal policy is a policy for which this function is maximized. We also have a kind of more advanced function. This is the action value function. Usually in the terminology of reinforcement learning, we will see it more. So it's defined not only based on the state, but also it depends on action. And we show it by Q, not by V. So it is a value of taking action A at state S under policy pi. And the definition is almost similar, except that we have this dependency to action. And so similarly, the optimal policy will be defined this way, the policy for which this function is maximum. So if in case that more than one action can maximize this Q, all of those actions are optimal, and so we can select one of them randomly. This is an example, the maze example. Suppose that we have an agent starts from this point and want to reach to this goal. And the bars are defined -1 at each step, except the last one, which is the goal, and we define as 0, which makes sense. After the training procedure that I haven't explained here about the training procedure, because it involves some mathematical stuff on the Q function or V function, we will have these values, and these are V pi values for each location of this maze. And based on these values, we can have the optimal policy. And the interesting point is that the optimal policy always is toward increasing this V pi value. For example, here we have -15, we have -16. The policy is from the more negative one into more positive one. So we have from -16 to -15. Again, if we, for example, look at here, we have -19 to -18. So there's a basic mechanism behind the training and finding optimal policy for reinforcement learning. How to find this optimal policy? So there are basically two methods for this optimization problem. One is dynamic programming, the other is temporal difference learning. And usually dynamic programming is used when we have a model of environment, but it's not always the case. We usually don't have the model of the environment. So environment is unknown to the agent. So we need to use temporal difference learning that doesn't depend on the model of the environment. And the most well-known method of temporal difference is Q-learning. You may have heard about that. If not, you'll see it later in the workshop. And when we code, we can get a better familiarity with that. So let me just postpone the questions. I have prepared some codes in Colab. So we have here, there is a Python library, which is called gem. And gem library is used for reinforcement learning. And here I have prepared Q-learning in gem, but I don't go through the training process because I just wanted to cover codes related to what I have talked about on the slides. So first, when you are in Colab, you need to install the package and you can import it as import gem. And you can initialize environment by creating, by using make. Here we use specific environment that exists in the gem. It's called mountain car -v0. And the states in this environment are made of two parts. So one is the x position, the other one is velocity. So we have negative velocity, which means that the agent is moving left. And also using this, we can find how many actions are defined based on this environment and agent interaction. So we have 0, which means left, 1, which means state, and 2, which means right.
Sorry, Armin, is it possible to share this link with everyone, or?
Oh, yeah, I can share it. Should I share it right now or after the talk?
It's up to you. Some people are asking in the chat, so.
Yeah, sure. Yeah, after I finish it, I will share it so they can work on it after.
Sure.
Yeah, and in each step, reward is defined as -1, and if the agent reaches to the final point, which is the success for the agent, it will receive reward 0. So it makes sense. And as we talked on the slides, reinforcement learning is a sequential process. So to define it, we need to have some kinds of iteration. So gem library has defined this environment.step function in order to make us able to define specific move. So the agent makes an action and we will have reward and the new state as the output. So if we run it into a loop in this way, we can and we print the reward and the new state. We see here a number of values. So as we talk about, the reward is always -1, and the states are made of 2 components. So this one is the x position, and this one is the velocity. So by default for gem, the maximum number of steps is 200. You can change it if you like. Or if before 200 it reaches to the target point, so the iteration will not continue anymore. And you can also find the minimum and maximum value of the states. So this code shows maximum and minimum value of a state. In the future, when we want to use Q-learning, we need to really discretize the state values if they have a large range of continuous state values. So for this procedure, if for example we want to make 20 buckets, and I have, for example, 0.6 and minus 1.2 as the max and min of the x position, and 0.0 and minus 0.07 as the maximum and minimum of the velocity. We can make a 20 by 20 grid of state values. And we have the third dimension, which is action. So the Q table, which is used for Q learning, is action is the Q value at specific state and for a specific action. So when we have a Q value of, for example, 0.8 at specific state and specific action, it means that we have a Q table, and you can find the value of a state and action into the table and the assigned Q values there. So you can also, based on the defined buckets, you can also make this Q table in this way. I will share the code, and you can play with the Q table. So the rest of the stuff, I put it for the next week workshop because they are more related to the training. But if you're interested to read it more, there is a reference at the end of this Colab code, and you can check it out more details. Thank you.
Great. So I don't know if you want to post it in the chat now so that people who are
let me unshare my screen, and then I will send it.
And if anyone has any questions, please ask now.
Yes, Amin, I have a question for you.
Yeah, sure. Just one. Want to share it here?
Yes, I take your time.
Yeah.
Okay. Yeah. Okay. So my question is, what should be the initial ratio between a random action or a calculated action?
So this happens during the training. When we want to train a reinforcement learning model, we have two things called exploration and exploitation. It means that if we select the action completely at random, so there is no strategy behind that, right? It means that it doesn't depend on the policy. So this phase is called exploration. And what's the benefit of that? The benefit is to find states in the environment that are not already seen. Maybe there's some places in the environment that the current policy doesn't capture them. So this is the reason for exploration and random action selection. And we have exploitation. Exploitation happens when agent interacts to the environment based on the policy that is learned till that moment. And it's basically a procedure that updates the Q value. So when it performs the action based on the reward that it receives, it updates the Q value. So using exploration and exploitation, the whole reinforcement learning procedure can be updated, and the optimal policy can be obtained.
And what should be the ratio? Like 50%?
Or
more?
Switch between exploration and exploitation.
Yeah.
Yeah, you can set the ratio. It's completely up to you, but for one of the projects I work on, yeah, I consider it 0.5. Yeah, which is
0.5. Okay. And like later in the life of the game, you want to decrease the random action.
Yeah, I think you can put it in a loop, something like when you use grid search, you can iterate for different ratios and see which one works better.
But so later you want to decrease the number of random action, but how do you like a skeptical like reason or timing when you want to decrease it, or
when the optimal policy was found, so you actually have the model prepared, so you don't need to use random action selection. So you remove the exploration phase and predict based on only the exploitation.
okay, yeah. Thank you.
Yeah, the predictions are always based on the exploitation.
Armin, is it possible to give access to everyone? You can share it and then give access everyone with the link.
I shared it.
Yeah, you shared it, but you didn't give access to everyone. If you can just on the setting of the share, so you can give access everyone with the link.
Yes. So
thank you so much.
Anyone else has a question to wrap up with Armin?
Can I ask another question?
Sure. Then there's no one else. Go ahead, Simon.
Okay, a small question. Can you use the library sklearning like Mo use it?
I never scikit-learn for reinforcement learning.
Yeah, can you use exactly?
Yeah, your question is if you can use scikit-learn for reinforcement learning?
Yeah.
I didn't see anything in scikit-learn about reinforcement learning. Actually, myself, I coded from scratch, but currently you can use a gym library, which is for OpenAI, but also you can search for the because there is not only one library for reinforcement learning. Other can search for them, but I think scikit-learn is not the one.
Okay, thank you.
Any other questions? Est-ce qu'il y a d'autres questions?
Can we measure performance on reinforcement learning models? It depends on the environment. Actually, it's a good question. For example, in the environment that I showed with obstacles and foods, the performance is measured based on the number of steps from the starting point until the agent reaches to food. So it is expected that when the number of steps is decreased, the performance will increase. So it depends on the type of problem that you define, and you should really see what kind of environment you have.
Amazing, amazing. Well, if some of you think of a question, feel free to reach out to Armin on Slack or post your question in the main Slack channel where we'll answer them promptly. Thank you so much, Armin. Very informative and very well explained and a good pace.
Thank you.
So thanks for that.